Hello everyone, welcome back to Bamane Pharm Lectures, where we make pharmacy simple. And if you have ever wondered how intravenous fluids, eye drops, and oral solutions are made safe for human body, this is your lecture. In today's lecture, we shall be learning about osmolarity. And if you're new to this channel, my name is Bamane and I am a tutor. Osmolarity simply means osmotic pressure. And from our previous lectures, we said that body fluids have got a certain osmotic pressure. And before any intravenous fluid or eye drops are administered, those solutions should be made isotonic with blood plasma. And isotonicity, every time we talk about it depends entirely on osmolarity of such a solution. So pay much attention as I take you through osmolarity, and by the end of this lecture, you'll be able to enter into the practical room or sit for any theory paper containing any calculation requiring you to make any interconversion between other units of measure and osmolarity. And where you don't understand, drop your concern in the comment section. I'll be grateful to help you understand better so that you can excel in your exams. Osmolarity. Osmolarity is osmotic pressure. And it is a very important biological process that is involved in the infusion of solids or transfer of fluids through a semi-permeable membrane. We know osmosis is all about passage of fluids or solids across a semi-permeable membrane. So that means our blood cells are based within a certain fluid, and that fluid has got a certain osmotic pressure. So if you administer a fluid which has got a different osmotic pressure compared to that of the body cells, it means that we are going to create an osmotic a concentration gradient. And when we create a concentration gradient, it means that there will be influx or exflux of fluids in and out of the cell. So to avoid that, all solutions that are made to be introduced directly into the bloodstream, they should be made isotonic with blood plasma to avoid unnecessary damage and also irritations, and also for the safety of the patient. So, intravenous solutions that are made for replenishment of fluids, say nitrates or electrolytes, and osmotic uretic mannitol are required to state the osmolar concentration. So, every intravenous fluid in their label, they should have the osmolar concentration of such a fluid such that it can indicate any practitioner that either this solution is isotonic with blood plasma, is hyperosmotic or hypotonic, so that we can make necessary adjustments to ensure that before such a fluid is administered to the patient, it is safe or it does not cause massive damage to body cells. Therefore, the concentration of osmotically active particles, which we may call ions or molecules, ions for those substances that dissociate in solution to produce particles, and molecules for non-electrolytes, like the likes of dextrose, boric acid, and so many others, as we covered them in our previous lectures. They are expressed in terms of osmol or milliosmoles. Milliosmol is simply a thousandth of osmol. A thousandth of osmol is mOsmol. So every time we talk about mOsmol, we mean a thousandth of osmol. So these particles are expressed in terms of osmol, and therefore 1 osmol is equal to 1,000 milliosmoles. And at all times, don't forget that relationship. Osmotic pressure is also proportional to the total number of particles in the solution, and you can know very well the time we are covering relationship between milli equivalents and millimoles. We say that milli equivalents depends entirely on electrical charge, whereas milliosmoles depends on the number of particles in that particular solution. So, osmolarity depends entirely on the number of particles in that solution. And the units that is mostly used to measure osmotic concentration or osmolarity is what we call milliosmoles, for short, mOsmol. So every time you see the word mOsmol, we mean milliosmoles. And this is the unit of measure for osmolarity. Therefore, for example, for substances that do not ionize or non-electrolytes, like dextrose, 1 millimole, which we may call 1 formula weight in milligrams, is equal to 1 osmol. For substances that do not dissociate in solution, 1 millimole is simply equal to 1 mOsmol. And if we take assumption that sodium chloride dissociates completely into a solution, it means that such substances that dissociate to produce 2 particles. Like for example, when sodium chloride is dissolved in water, it ionizes in solution to produce sodium ion and chloride ion. And when you add this, you come up with 2 particles. So such substances, 1 millimole represents 2 milliosmoles. And those substances that when dissolved in water and produce 3 particles, like the likes of calcium chloride. When calcium chloride is dissolved in water, it is going to be composed to produce calcium ions plus 2 chloride ions. When you add the 2 chloride ions plus the 1 calcium ion, you get 3 particles. So particles that dissociate in solution to produce 3 particles, 1 millimole represents 3 mOsmols. Therefore, we need to know at all times that when a substance do not dissociate, the number of millimoles and mOsmols are the same. Like for the case of dextrose, 1 millimole is equivalent to 1 mOsmol. But when substances dissociate in solution to produce, say, 2 particles, 1 millimole will give us 2 mOsmols. And if it produces 3 particles, 1 millimole will give us 3 mOsmols. Therefore, the concentration of a solution may be expressed in terms of either osmolarity or its osmolarity. When we say osmolarity, we simply mean the number of mOsmols of a solute per liter of solution. The number of mOsmols of a solute per liter of solution. And when we say osmolarity, we simply mean the number of mOsmols of solute per liter per kilogram. This is per kilogram of solids. The difference between these two is that when we are talking about osmolarity, we mean number of mOsmols of a solute per liter of solution. But when we talk about osmolarity, we mean mOsmols of a solute per kilogram of the solvent. Therefore, the mOsmolar value of separate ions of an electrolyte may be obtained by dividing the concentration in milligrams per liter of that ion by its atomic weight. We shall look at this when we look at our first example, and we see how we can come up with that such an expression. And therefore, we should note at all times that the normal serum osmolarity ranges between 275 and 300 mOsmols per liter. And the other thing we need to note at all times is that osmolarity is measured in liter. So every time you're calculating for osmolarity, the answer should always be in liters. Therefore, we need to see how can we really calculate for osmolarity. So many times students get confused with formulas. Sometimes how you can transfer from first principle and you arrive at the answer. Today, pay very keen attention so that you can understand how we can use both methods, first principle and also from the formula, to come up with the formula for all answers concerning osmolarity. Let's drive the example. Osmolarity can be calculated from the formula osmolarity in mOsmols per liter is given by concentration divided by molecular weight times I times 1,000, where concentration is in grams per liter and molecular weight what sometimes for short we say MWT is in grams per mole. The I value simply means number of particles. Then 1000 we multiply by 1000 to convert osmol per liter to mOsmol per liter. So in short, the formula becomes osmolarity, which is mOsmol per liter, is given by concentration in grams per liter divided by molecular weight times number of particles being multiplied by 1000. At all times, you should have this formula at your fingertips. Let us look at the first example. Our first example. Calculate the osmolarity of 0.9% weight in volume sodium chloride injection. The first thing to do before you can do any other thing is for you to note that osmolarity, call it mOsmol, is calculated in liters. After knowing that, we want to convert this into mOsmols. But remember, in our previous lecture we said, when we have the mass, we convert the mass to moles. Then we convert the moles to millimoles. Then finally, we convert the millimoles to mOsmols. So we are going to begin by calculating the number of moles of sodium chloride. But remember, when they say 0.9%, they simply mean that we have 100 mils of solution contains 0.9 grams of sodium chloride. But we are saying that osmolarity is calculated in liters. But whenever we say liter, we mean 1000 mils. So how about the 1000 mils of solution? It will contain 0.9 grams over 100 times 1000. And when we compute this, we shall get 9 grams per liter of sodium chloride. So we have gotten the amount of sodium chloride in 1 liter. So we need now to convert the mass we have into moles. But remember, they have given us, we know that the molecular weight of sodium chloride is 58.5 grams per mole. So what we know in this case is the mass. Because we need to get what is in this mass. We have the molecular weight, which is grams per mole, and what we want is the mole. So we are going to first do it from first principle, where we shall say that 58.5 grams of sodium chloride contain 1 mole. How about the 9 grams of sodium chloride? Will contain 1 out of 58.5 times 9. And when we compute this, we shall get 0.1539 moles. So we have gotten the number of moles of sodium chloride, which is equivalent to the 9 grams. So we are going now to convert the moles we have obtained into millimoles. But we know from our previous lecture that 1 mole is equivalent to 1000 millimole. How about the 0.1539 1.39 moles will be equivalent to 1000 times 0.1539 divided by 1, and all this is in millimole. And when you compute, we shall get 153.8, which is approximately 154 millimoles of sodium chloride. But remember our question, and this is in a liter. But remember our question, we need to calculate osmolarity. But whenever we say osmolarity, we mean mOsmol per liter. So we are going to say, remember, we say that for those substances that ionize, produce two particles. We saw that sodium chloride dissociates in solution to produce sodium ion plus chloride ion, and these are two particles. So any substance that dissociates in solution to produce two particles, 1 millimole is equal to 2 mOsmols. Therefore, the 154 millimoles will be equal to 2 times 154 divided by 1. This will give us 308 mOsmols per liter of sodium chloride. That is if we are calculating from first principle. Let us also see how can we calculate it using the formula. I hope you have noted this down. Let us also see how we can calculate this using the formula. And please, if you find this video very useful, like the channel, share it with your friends and classmates, and also subscribe to the channel to keep it growing, and also to keep you updated with more simplified pharmacy calculations. So from the formula, we say that osmolarity is equal to grams per liter divided by molecular weight times number of particles being multiplied by 1000. We say multiplying by 1000, we are simply converting osmol per liter to mOsmols per liter. But we have already obtained the amount of sodium chloride in a liter, which was 9 grams per liter. So we shall simply substitute, where here we have 9 grams being divided by the molecular weight, which is 58.5, times number of particles, which is 2, being multiplied by 1000. And when you compute this, we shall also still get 308 mOsmols per liter of sodium chloride. So, in case you have a question in objectives, it is easier to use the formula. But meanwhile, you can also use first principle. Let us look at the second example. In our second example, you can feel free to pause this video and calculate it out and see whether you can get the same answer with me. In our second example, a solution contains 156 milligrams of potassium ion per 100 mils. How many mOsmols are represented in 1 liter? And the question is, here they have been specific. They have simplified it for you because they have already told you in a liter. In certain questions, they may not specify it, but you should at all times remember that mOsmol is calculated in liters. So let us calculate this. First of all, they are telling us that we have 156 milligrams per 100 mils of the solution. So the first thing is to convert this mass into a liter. But we know that 100 mils of the solution contain 156 milligrams. How about the 1000, which is the liter? $100 mils of solution will contain 156 milligrams divided by 100 times 1000. And when you compute this, you shall get 1,560 milligrams of potassium ions per liter. So, but remember, from our formula, we need to convert the mass we have obtained into grams. But we know that 1 milligram is equivalent to 1 out of 1,000 grams. How about the 1,560 milligrams? This will be equal to 1 out of 1,000 times 1,560. And when we compute this, we shall get 1.56 grams of potassium ions per liter. So after getting the number of potassium ions in a liter, we can do from first principle, where we know that the molecular weight of potassium, which is 39 grams per mole. What we know is the mass. So we shall say 39 grams of potassium ion contain 1 mole. How about the 1.56 grams of potassium ion? This will contain 1 out of 39 times 1.56. When you compute this, we shall get approximately 0.04 moles of potassium ion per liter. Now, after obtaining the moles of potassium ions in a liter, we are also going to convert these moles into millimoles. But remember, we said 1 millimole is equivalent to 1,000. Is equivalent to 1,000. 1 mole is equivalent to 1,000 millimole. How about the one we have obtained here, the 0.04 moles? This will be equal to 1,000 divided by 1 times 0.04. And when we compute this, we shall get 40 millimole. So we have 40 millimoles per liter of potassium ion. But our main aim, we want to calculate how many mOsmols of potassium ion are in a liter. But remember, we said this is simply 1 ion. So we shall say 1 millimole of potassium ion contain or is equal to 1 mOsmol. How about the 40 millimole? It means it will also be equal to 40 mOsmol per liter. So the number of mOsmol per liter will be 40. So I want you to use the formula and see whether you can come up with the same answer. Let us look at our third example. The third example, a solution contains 10 milligrams percent of calcium ions. How many mOsmols are represented in a liter of solution? The molecular weight of calcium ion has also been given. This is your assignment. Pick up your calculator and a pen and try to solve this question using both first principle and also from the formula. And the answer you get, drop it in the comment section. I'll be right to tell you whether you got it right. And if not, I'll be grateful also to help you understand better. And if you have any question about osmolarity, feel free to raise it in the comment section. I'll also be grateful to help you. Thank you for watching. Please like this video and share it with your colleagues and also your classmates. And don't forget to subscribe to this channel to keep you updated with more simplified pharmacy lectures and also to keep our channel grow. Let us catch up in the next lecture. I hope you have mastered osmolarity.